Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. We will continue on the topic of molecular mechanics and force fields. I showed you different types of functional forms of force fields, MM2, MM3, then CV, FF, charm and so on. So, some of the force field terms have quadratic, that means R minus R naught square, or quartic, even R minus R naught raised to the power 4. Sometimes Morse form, that is exponential form, is also used. So basically force field contains terms related to bond stretching, angle bending, torsion and non-border interactions. Those include electrostatic forces, van der Waals forces, hydrogen bonds. So we looked at different forms of force field, and then I also mentioned about boundary conditions. Okay, we can model the molecule in the form of a vacuum. That means there are no solvents, nothing around it, the molecule is all alone, maybe it is in vacuum or it is in a gas phase, or we can consider solvent surrounding, one layer of solvent, two layers of solvent, many layers of solvent, or we could even consider a periodic box. That means as I mentioned before, it is a rectangular box or a square box, the molecule is inside surrounded by lots of waters, and we assume similar box on all the 6 faces of this rectangular box or the square box, and then if a water molecule goes out, then another comes in from the opposite direction, so that the density is maintained constant. That is called periodic box, and generally periodic box is preferred when you are doing molecular dynamics type of situation, and also if you want to look at protein folding, unfolding and so on. Okay, now you have the molecule, you have the boundary condition, but you need the molecule to attain certain minimum energy conformation. Okay, that is called minimum energy thermodynamically stable conformation, because all systems like to attain a minimum energy conformation at that particular set of condition, whether it is density or temperature, pressure and all that, and that is called a stable structure. Okay, whereas transition states will be saddle points, that means they are not very stable, but only the minimum energy conformation may be stable. For example, look at this graph. So if I am changing certain bond distances, energy may be coming down, there could be many minima, we call these the global minima, we call these the local minima. So you may start with a single conformation of the structure, we keep changing the angles, the lengths and so on, so that the energy keeps going down, and hopefully we want to reach here. You may be starting from here, you want to reach here, you may be starting from here, you want to reach there. Okay, so these are called local minima, whereas this is the global minima. The main challenge in molecular modeling is to find the global minima, that is as you keep changing the conformation, energy will come down and down and down, and not stuck in a local minima. Okay, so this process is called energy minimization process. You may start with one conformation, and as you change the features, bond length, bond angle, torsion, energy may be coming down, but you do not want to end up here, because this is a local minima, you want to end up here. So softwares start with different conformations and hopefully try to see whether they are able to reach the global minima. That is the biggest challenge in finding out the minimum energy conformation of a molecule. Okay, so again once more, this is called a local minima. For example, if I have a ball, I just drop it, it will come here. Okay, whereas if I have a ball here, it will come here. If I have a ball here, it will come here if I drop it. Okay, so the balls, if they are dropped very slowly, it will invariably end up here, unless the energy is high enough for the ball to cross and go the other side. So you may start at different starting conformations and see how the minima is reached, okay, and you will get different minimas and select the minimum of the minimum, and we call that global minimum. Generally for small molecules it is not very difficult to attain global minimum, but if you are talking about large molecules like peptides, proteins, it is very difficult to attain a minimum energy conformation. Okay. So we need to have the minimum energy conformation because that gives you the 3-dimensional shape, size, the polar surface area, the volume, and so on. Actually there are many softwares, commercial softwares available in the market. There are many free softwares available in the market. You do not need to use a commercial software, it is good enough to use a free software. One of them I am going to show you, that is called Marvin, okay. Okay, that is called Marvin Sketch. So you have to go to the site and then you have to download that software, and then maybe you have to register before you start using it. So you can register as a student or a faculty, it is free, okay, it is completely free, you do not need to pay anything, but you have to register in that software. That is called it's belongs to this company, but it is a free software, but you have to register as a student or as a faculty. In Marvin Sketch we can draw structures, sketch the structures, okay, and then we can use it, or we can take mol files or SDF files downloaded from Zinc, and then we can upload here and so on. For example, this is the sketch option, you got a lot of things here. Okay, imagine I am drawing a benzene, and then I am connecting it with the different bonds, okay. I'm putting a double bond there. So I am making a ketone here, as you can see. Then I put again a double bond there, then I am putting a single bond there, and then I am adding another benzene here. Okay, so we have a benzene here, we have a ketone alpha beta unsaturated, this is called chalcones. Chalcones are molecules which have good antioxidant property, antibacterial property, and so on, okay. So we can make the structure into, put it in a 3-dimensional form, so it becomes in 3-dimensional form, as you can see. Okay, we can rotate it in 3D, as you can see here. Now the molecule is in 3D form. We can shrink it or enlarge it, we can move it forward or backward, okay, so we can do all those things. Now we can even get the conformation of this molecule. How do I get the conformation? Let us go to calculations, then we can get conformations. You see conformers. I talked about force field, you remember this FF94 force field or draining force field. Imagine we will go to MMF4 and the energy is given in kilocalories per mole. Optimization, we do it normally, return only the lowest energy conformer, okay. So we just say okay. Okay, so we got the minimum energy conformation of this particular molecule is called chalcone. As you can see, the energy is 65 kilocalories. So we can rotate this molecule, the oxygen is there, there is a double bond here, okay, alpha beta double bond, there is a phenyl group, there is another phenyl group here, this is called chalcone. We can do a lot of data calculations. For example, I can calculate log P of this molecule, as you know, log P is most important, okay. We can give chemaxon type of log P, it gives you okay. Okay, so it is given log P, it is a highly hydrophobic, you can see 4.7, and this is called a group contribution method based log P. So all these carbons are given certain values, okay, and the oxygen gets a negative value, okay, as you can see this is the log P, okay, and you can see the ones which contribute towards, okay, this is called we can measure the log P. So this is called a group contribution method. So when you have a CH2 or a aromatic CH, they all contribute, so they all get added up, oxygen gets a negative, so it is given a negative value. So that is the log P. Now similarly we can do other calculations also, we can do geometry calculation, topology analysis, okay. So we can do lot of these calculations, have a look at it. Okay, so you can see how many aliphatic atoms are there, how many aliphatic bond counts you can see, right, aromatic atoms, okay, and then chain atom counts, aromatic ring counts, fused aromatic, so this is the distance degree, steric effect index, it is giving you the steric effect, as you can see here, it gives you the steric effect, and this gives you the eccentricity part of it, this is the degree of distance, so a lot of information on this, okay. Again we can look at pKa, just we can look at pKa here, for example this gives you the pKa of the molecule, okay, 2, okay, 2 it gives between pH of 0 to 13, 14, okay, so it gives you the pKa of this, but it gives you microspace distribution, species distribution at 2 different pH range. Then we can also calculate polar surface area, so it gives you the polar surface area is 17, it is quite low because only oxygen is the polar molecule, whereas remaining is our non-polar, okay. Then we can do other molecular surface area, so it gives you the molecular surface area, as you can see 320 angstrom square, the molecular surface area. This information can be stored for many more calculations. So we can look at the charge distribution, oxygen is the only negative that is going to be contributing, okay. So as you can see oxygen is the only thing, minus 0.41, okay, oxygen, many of them, all these are positive. Here again you get some minus on these carbons because you have a double bond, you see this red color that is negative, the blue color is more on the positive side. So we can see the charge distribution on the molecule, okay. So there are some negative regions here because of this the double bond here, okay, that is contributing to that, whereas this is totally positive. Then we can look at okay, we looked at geometry, geometrical descriptors, okay, I think we looked at that also, yeah. Okay, so we can as you can see here, it gives you the steric hindrance of this molecule, okay, the lower it gives the energy F4, this is based on the software, minimal projection area, maximal projection area as you project it on a 2-dimensional plane in both the directions, okay, as you can see here. Table options, elemental analysis, it gives you the CHN ratios, carbon, hydrogen, oxygen ratios. It also gives you the mass spectrum. This is mass spectrum theoretically calculated. So if I do a mass spec using experimental, I can always cross check. It gives you atom count, it gives you formula, molecular weight, also the mass spectrum, as you can see, molecular weight at 222, 23, 24 and so on. Actually it gives you a CHN ratio. So if I do a CHN analysis, I can cross check whether I get the same thing. Okay, then I can get a bond length. Okay, as you can see, you get the bond length here. Okay, quite long, 1.23. This is quite short. That's the ketonic bond. Okay, of course carbon hydrogen bonds are also very small, whereas carbon carbon bonds you can see 1.46. okay, the double bond is 1.34 here, carbon carbon double bond. Okay, aromatic bond 1.36. so we can get the bond length also. So a lot of calculations can be done. That's the beauty of it. Okay, we can get the energy using kilocal or kilojoule also. This software has only 2 force fields. There are softwares which have many force fields. Okay, okay, so it gives you 10 different conformations with the different energies. As you can see, this is a 66 kilocalories conformation. This is a 65 kilocalories conformation. Okay, 65 kilocalories. This is a 66 kilocalories. It gives you a confirmation of this count 1, count 2, count 4, then count 5, count 6. This is a 69 kilocalorie confirmation, as you can see here. The 67. So if I am looking at a minimum energy, I will go for maybe some 65. So this is the top, the best one, 65.01. So if you look at the 10th one, you will get 69.53, as you can see here. Okay, between this and this one, there are changes in the bond length or angle or torsion, so that there is a 4 kilocal, almost a 10% reduction in the minimum energy conformation. Okay, so we can look at large different types of conformation also, because conformations are important. If I am looking at the flexibility of the molecule, also how it docks to the active site. Okay, in such situation also it's very important to understand. Okay, so I had explained pKa, log P, charge. We can look at the charge distribution on the molecule, polarizability, okay, this is the polarizability of the molecule. Okay, as you can see, this is the polarizability of the molecule. Polarizability is a function of charge as well as the volume of the molecule. Okay, so many calculations can be done with this particular Marvin software actually. Okay, we can also do 3D alignments. If I have many molecules together, we can align it. I will show when we do something called a pharmacophore modeling. Okay, that's later on actually. Okay, okay, so one approach is by drawing the structures like I showed here. Another approach we can get it through zinc and Swiss ADME. Look at this. So I have, this is metformin. So how do I get metformin? Zinc database, as you know, we can get metformin. Okay, another approach maybe we can do it through the SDF approach. Yeah, so SDF itself we can open it using Marvin view. Okay, so it gives you the metformin. As you know, metformin has a lot of nitrogens here. Okay, and you can look at the log P. You will see very negative. because it is highly hydrophilic. Okay, log P 0.21 because a lot of nitrogen is here. Okay, so this nitrogen has minus 0.53, that's why it's very red, and there are many red colors here, minus, minus. So log P is quite negative when compared to the previous one which I showed you, where log P is almost 4. So again we can look at different aspects of metformin. We can go to the tools page, we can look at conformers. Okay, it gives you the best conformation of this molecule. Okay, so we got the best conformation of metformin. Okay, and then we can do the same calculations like I mentioned. Okay, so in this technique, what did we do? Here I got the structure from zinc database, the SDF, and then opened it using Marvin view. So you get this, then we can do all these calculations, getting log P's, getting charge distribution, looking at different conformations, topology analysis. We can look at hydrogen bond donor acceptors. Okay, okay, so it gives you the hydrogen bond donor and acceptor. As you can see, they are acceptors. Okay, generally they are only acceptors. Donor count, donor sites 5, acceptor count it's 5. Okay, because as you can see here, acceptor, 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 these are donor, donor, donor. So the NH can be a donor, the N can be an acceptor. Okay, as you can see here. Okay, so all the calculations, all the informations related to the molecule can be analyzed using this Marvin. So one approach is drawing the structures, another approach is to take it from the zinc database as an SDF file and open it with Marvin, and Marvin does it, and then we can do a lot of calculations. As you can see here, we can do a minimum energy conformation of the molecule. Okay, so a lot of things can be done with these tool options. We can look at this is called a clean in 3-dimensional, so we can look at and so on. Okay, so this particular software, the Marvin, is extremely useful for getting 3-dimensional conformation of various structures, getting information about the molecule related to the electrostatic, geometric, charge related information. We can then use these 3-dimensional structure for other calculations. Suppose later on I want to do pharmacophore studies, I can do that. And the beauty of it, I can draw these structures. Okay, I can draw the structures using this sketch pad and then take it for a 3-dimensional conformation. Okay, analysis. That's the beauty of this particular software, Marvin. And as I showed you, we can do so many different types of data analysis. Okay, that's the main advantage of this particular software. And there are many other softwares, free softwares, but this is one of the best ones I would recommend. And as I said, it's a free software. We don't need to have any payment on this. We just have to register and register as a student or a faculty and so on. So that's the advantage of this particular software actually. Okay. So getting the conformations, 3-dimensional conformations, minimum energy conformations is quite simple using freewares like I showed you this. So I would like you to explore on this Marvin further in your room, in your office. Okay, and you can get more information using this. So we can draw very complex structures also, or we can go to zinc database, and if the structure is available, we can download as SDF and then take it to Marvin view and then do all the calculations and store it in MRV format for further analysis, because later on we are going to study pharmacophore analysis, where this particular information will be very essential. Okay. And okay, we will close this. Okay, so as I have been telling that getting the confirmation is a big challenge of a particular molecule. Okay, you may end up with the local minima most of the time rather than global minima. So you may have to start with the different starting confirmations so that you end up with the local minima. I mean, you skip the local minima, end up with the global minima. There are many other approaches which are suggested. We will talk about it in the forthcoming classes to see how to arrive at the global minima, not get stuck in the local minima. Generally for small molecules you may be able to reach global minima, but if you have big molecules, this type of minimum energy confirmation analysis is quite difficult, okay, because it is going to be very time consuming. There could be millions of possible confirmations, and you might not be ending up at the global. You may be getting stuck in the local here. It is like a car, if it comes down the slope. So there are many techniques available. We will talk about it as we go along, okay, and those techniques are simple, complicated and time consuming, but it is very essential for us to understand the three-dimensional confirmation of molecules, because it is very important to understand the minimum energy confirmation of a molecule, because the molecule may attain that confirmation when it is in a stable state, and at sometimes when it goes into the active site of the protein, it may like to modify its three-dimensional minimum energy confirmation also, okay, depending upon the interaction it has with the active site. So we will talk more about the confirmation analysis in the next class as well. Okay, thank you very much for your time.